A star exists that could swallow our sun and every planet in a single gulp. These are the universe's most massive stars, cosmic titans, whose very existence bends the rules of physics. By the end of this journey, you will understand how these stellar giants shape everything from the atoms in your body to the fate of entire galaxies. We will uncover how a star can weigh over 250 times more than our sun yet vanish in a cosmic blink, and what mysterious force might finally stop a star from growing any larger. What does the life of a true cosmic giant look like? But before we can truly grasp the power of these stellar giants, we need to understand their sheer scale. The term most massive is often used, but it has a very specific meaning. A star's mass is its weight, the total amount of matter it contains, which dictates its gravity, its life, and its violent death. This is different from its physical size or volume, which is how much space it takes up. A star can be incredibly large but relatively light, a vast, puffy balloon of superheated gas. To find the champions of pure physical size, we look to stars like UY Scuti. This is a red supergiant, one of the largest known stars in the universe by sheer volume. Its dimensions are so vast they defy easy comprehension. If you were to pluck UY Scuti from its home and place it at the very center of our own solar system, its searing surface would not stop at Mercury or Venus or even Earth. It would swallow Mars whole and continue outward until its outer layers brushed past the orbit of Jupiter. That single star would fill our entire inner solar system. To put that in another perspective, you could fit over 1,700,000,000 of our suns inside the volume of UY Scuti. Yet, for all its staggering size, pinning down the exact title of largest star is surprisingly difficult. These objects are unimaginably far away, they pulse and change in brightness, and their outer atmospheres are wispy and indistinct, like trying to measure the exact edge of a cloud from thousands of miles away. Different measurement techniques can yield different results, which is why the crown often shifts between a handful of colossal contenders. This uncertainty itself is a clue, hinting at the turbulent and dynamic nature of these cosmic behemoths, whose very forms are a constant battle between outward pressure and crushing gravity. Yet despite their breathtaking size, stars like UY Scuti are not the ultimate champions of cosmic power. For that title, we must look beyond volume to the raw, concentrated force of mass. And here, the undisputed heavyweight champion of the known universe is a star with a name that sounds like a serial code, R13601. This stellar monster resides not in our quiet galactic neighborhood, but in a cosmic furnace known as the Tarantula Nebula, a vast stellar nursery in a neighboring galaxy. Within that chaotic cloud of gas and dust, R13601 stands alone in its sheer physical weight. Its mass is a staggering number, over 250 times that of our Sun. Picture our entire solar system, the Sun and all its planets, asteroids and comets. Now imagine gathering that much material, and then repeating the process 250 more times and crushing it all into a single, seething sphere of plasma. That is the scale of this star. Its existence pushes against a fundamental law of stellar physics called the Eddington limit. This is a theoretical barrier, the point at which the outward pressure from a star's own radiation becomes so intense that it begins to blow the star apart from the inside out. A star shining too brightly would literally tear its own outer layers away. R13601 dances perilously close to this limit. It is so massive and so hot that it shines with a ferocity almost beyond comprehension, blazing with the luminosity of millions of our suns. Its light is not a gentle glow but a hurricane of radiation, a constant, violent stellar wind that carves and sculpts the very nebula that birthed it. This star does not simply exist within its environment, it dominates and reshapes it, proving that in the cosmos, true power is measured not by how much space you fill, but by the sheer, crushing weight of your presence. Such extreme mass demands an equally extreme birthplace. A star like R13601 could never form in the quiet, sparse regions of space. It requires a cosmic forge of unimaginable density and violence, a place known as a stellar nursery. Picture the Orion Nebula, that faint, fuzzy patch in the hunter's sword visible from Earth. Through a telescope, it is not a serene cloud but a churning, luminous cauldron of gas and dust lit from within by newborn stars. This is a giant molecular cloud, a cold, dark structure so vast it could contain 10,000 solar systems. Within these clouds, gravity works its slow magic, causing denser knots of material to begin collapsing inward. For a star destined to become a true titan, this collapse is not a gentle gathering. It is a frantic, chaotic race against time. As the core of the protostar heats up, it will eventually ignite nuclear fusion and begin to shine. That first light is a death sentence for further growth because the radiation pressure starts pushing the surrounding gas and dust away. So the star has only a brief window, perhaps just a few 100,000 years, to gorge itself on material before its own power cuts off the food supply. How does it manage to eat so much so fast? Astronomers are still piecing together the answer, and two compelling theories paint a picture of a violent stellar childhood. The first is called monolithic collapse. Imagine a single, incredibly dense knot within the cloud, so heavy and unstable that it falls inward in a rapid, coordinated collapse, funneling a vast amount of mass directly into the growing core almost all at once. The second theory, competitive accretion, is even more dramatic. Here, many smaller stars begin forming close together in a crowded cluster. They all pull from the same reservoir of gas, but the biggest ones, with stronger gravity, begin to steal food directly from their smaller siblings, bullying their way to monstrous size. In both scenarios, the newborn star is surrounded by a whirling, flattened disk of leftover material called an accretion disk. This disk is the star's final meal ticket, a spiraling highway of gas that feeds the growing core even as the star's fierce radiation blows away the cloud above and below it. The formation of a massive star is a precarious balancing act, a desperate scramble to eat enough before the table is violently flipped over by the star's own awakening power. This frantic race to gather mass sets the stage for an entire lifetime of urgency. A star's lifespan is a direct consequence of its weight, and the universe's most massive stars are the ultimate cosmic spendthrifts. Our own Sun, a stable, middle-class star, has a fuel tank designed to last for roughly 10 billion years. It is a model of stellar frugality, fusing hydrogen into helium at a steady, measured pace in its core. We are currently only halfway through its life, a testament to its moderation. A truly massive star, however, lives by a different code. It possesses a fuel tank that is vastly larger, but its engine is cranked to unimaginable extremes. A star just 10 times the mass of our Sun will blaze through its entire supply of hydrogen fuel in a mere 20 million years. That is not even a blink in the cosmic calendar. And for a true titan like R13601, with over 250 solar masses, the timeline becomes breathtakingly short. Its entire brilliant, turbulent existence, from birth to its inevitable cataclysm, may last only 1 or 2 million years. To put that in perspective, if the entire history of our Sun were compressed into a single year, a star like R13601 would be born, live its entire life, and die in less than a single afternoon. This is the ultimate live fast, die young stellar philosophy. The reason for this frantic pace lies deep within the star's heart. The immense weight of all that overlying material creates crushing pressures and temperatures in the core far beyond anything in our Sun. This turns the core into a runaway nuclear furnace. The star does not merely burn its hydrogen fuel, it devours it in a desperate, furious fusion reaction. The outward pressure from this incredible energy output is the only thing holding the star up against its own gravity. but once the core exhausts its hydrogen, the balance shifts. Gravity squeezes the core tighter, heating it until it can begin fusing the next available fuel, helium, into carbon and oxygen. This process repeats, but each new fuel burns faster and hotter than the last. For a massive star, this is a desperate sprint through the periodic table. In its final days, the core becomes a layered onion of elements, with silicon fusing into iron at the very center. Iron is the ash of nuclear fusion, a dead end. It cannot release energy by fusing, so it simply accumulates, sealing the star's fate. This breakneck journey from hydrogen to iron might take our sun billions of years. For a stellar giant, it happens in a geological instant, a spectacularly violent life spent in a blinding flash of cosmic glory. This furious sprint through its nuclear fuel transforms the star's core into a layered cosmic forge. While our sun relies on the relatively slow and steady proton-proton chain to fuse hydrogen into helium, a massive star's heart is so intensely hot and pressurized that it switches to a far more powerful engine, the carbon-nitrogen-oxygen cycle. Think of it as the difference between a campfire and an industrial blast furnace. The CNO cycle uses carbon, nitrogen, and oxygen as catalysts to fuse hydrogen at a dramatically faster rate, generating a torrent of energy that makes the star shine millions of times brighter. This incredible heat and pressure create the conditions for a remarkable process, one that builds the very elements that make up our world. As the star burns through one fuel, gravity crushes the core further, igniting the next. The core becomes a layered onion, each shell fusing a different element. After hydrogen becomes helium, the helium ash itself begins to fuse, creating carbon and oxygen. Then carbon fuses into neon and magnesium, neon into oxygen and magnesium, oxygen into silicon and sulfur, and finally, silicon fuses into iron. Each step happens faster than the last, with the final silicon burning stage lasting perhaps only a single day. In this way, the star manufactures the raw materials of planets and life itself. Nearly every atom of carbon in your body, the oxygen you breathe, the calcium in your bones, and the iron in your blood was forged in the heart of a star that lived and died long before our sun was born. Massive stars are the universe's primary producers of these crucial elements, scattering them into space in their final, violent acts. Yet iron marks a deadly turning point, the end of the line for this stellar factory. Iron is a cosmic dead end, and its silent accumulation at the star's core spells doom. But the star's outer layers are already engaged in a spectacular, ongoing rebellion against the crushing gravity below. This is the era of stellar winds, a hurricane of radiation so fierce it literally blows the star apart piece by piece. The engine for this self-destruction is the star's own unimaginable luminosity. Remember, a star like R13601 shines with the power of millions of suns. This light does not simply travel outward, it carries a physical force, a relentless radiation pressure that acts like a constant gale pushing against the star's outer atmosphere. For these massive stars, this outward push is so overwhelming that it overcomes gravity's pull on the tenuous outer layers. The result is a stellar wind, a supersonic torrent of charged particles blasting away from the star at speeds reaching millions of miles per hour. This is not a gentle breeze, it is a continuous, catastrophic mass loss event. The star is evaporating into space, shedding entire solar masses worth of material over its short lifetime. No star demonstrates this violent process better than the infamous Eta Carinae, a volatile binary system in our own galaxy. In the 1840s, Eta Carinae underwent a titanic eruption, becoming for a time the second brightest star in the night sky. Astronomers believe this was not a supernova, but a colossal stellar tantrum, a hyperactive episode of mass loss where the star ejected material equivalent to 10 or even 20 times the mass of our Sun in just a few years. That ejected material did not simply vanish. It formed a breathtaking structure known as the homunculus nebula, a twin-lobed cloud of gas and dust that now encases the star, glowing from within by its ferocious light. This beautiful nebula is a tombstone for the star's own lost flesh, a direct snapshot of its self-inflicted violence. This relentless stripping has a profound consequence for the star's ultimate fate. By blowing away its own outer hydrogen and helium envelopes, the star is effectively on a race to see what dies first, the fusion engine in its core or its own body. The mass lost to these winds determines the final weight of the iron core that will eventually collapse. A star that sheds enough of its envelope can completely change the type of explosion it will produce, transforming what might have been a universe-shaking cataclysm into something quieter, or perhaps something even more strange and exotic. The silent buildup of iron and the furious stellar winds set a timer, but they also raise a profound cosmic question. Is there a final, absolute ceiling to stellar growth? Could a star somewhere in the distant cosmos weigh 500 or even 1,000 times more than our Sun? This is the mystery of the upper mass limit, a frontier where theory and observation collide. The guiding principle for decades has been the Eddington limit, named for the astronomer Arthur Eddington. It is an elegant idea of balance. A star shines because of fusion in its core, and that light exerts an outward pressure. Gravity pulls inward. For a star to be stable, these two forces must be in equilibrium. The Eddington limit marks the point where the outward radiation pressure from a star's own luminosity would become so overwhelmingly strong that it overpowers gravity, literally blowing the star's outer layers into space and preventing it from accreting any more mass. It is a theoretical speed limit for starlight and by extension for stellar mass. Based on our standard models, this limit was long thought to sit around 150 solar masses. And then we found R13601 clocking in at over 250. Its very existence is a glaring challenge to our textbooks. How can this star be so massive and so bright without immediately tearing itself apart? The answer may lie in its composition and structure. Stars like R13601 are not just scaled-up versions of our Sun. They are almost pure hydrogen and helium with very few heavier elements, which makes their internal opacity lower. This allows radiation to flow outward more easily, reducing the pressure buildup that would otherwise rip the star apart. Think of it like a sieve versus a solid wall. The star's structure lets the intense energy escape more efficiently, granting it a temporary reprieve from its own self-destructive power. But even with this advantage, astronomers suspect there is still a wall. Current theories suggest the absolute upper limit for a star forming from a single collapsing cloud might be around 300 solar masses. Beyond that, the forces of self-destruction would be insurmountable. Yet, nature has another, more violent path to creating supermassive stars, stellar mergers. In the dense, crowded nurseries where these giants are born, stars can swing too close to one another. A close binary system can spiral inward over time, culminating in a cataclysmic collision. When two massive stars merge, they can create a single, even more monstrous object, potentially breaching the 300 solar mass barrier in a single, violent event. This makes the hunt for these extreme objects not just a cataloging exercise, but a direct test of our understanding of stellar physics. Every new candidate, every extreme measurement, forces us to refine our models of how matter behaves under the most extreme conditions the universe can produce. The search for the ultimate heavyweight champion is in essence a search for the outer edges of physical possibility. The search for stellar giants often reveals a surprising truth. These titans rarely live in solitude. Far from being isolated monarchs, the most massive stars are frequently found in tight binary or even multiple star systems, locked in a gravitational dance so intimate it defies our solar system's experience. This cosmic companionship is not a peaceful one. It sets the stage for a phenomenon as dramatic as it is destructive: stellar vampirism. When two massive stars orbit extremely close together, their gravitational fields create a complex landscape of influence. The stronger gravity of the more massive star can begin to distort and pull material directly from the atmosphere of its companion. This stolen gas, rich in hydrogen, flows across the space between them in a stream called an accretion disk, funneling fresh fuel onto the surface of the greedy primary star. The effects are transformative. The vampire star, gorging on this new hydrogen, can appear rejuvenated, its outer layers refreshed, making it look hotter, bluer, and younger than it truly is. Meanwhile, its victim is stripped down, robbed of its outer envelope to reveal a hotter, helium-rich core prematurely. This violent exchange completely rewrites the evolutionary script for both stars. The donor star, now less massive, may live a longer, quieter life than originally destined, while the vampire, having bulked up even further, races even faster toward its own explosive demise. In extreme cases, this process can lead to outcomes stranger than any fiction. If the donor is a red supergiant and the vampire is a dense neutron star, the neutron star could spiral right into the supergiant's core, creating a theoretical hybrid known as a Thorne-Zitkow object, a red supergiant with a neutron star heart. Even more directly, this stellar cannibalism can set the timer for a spectacular double blast. If the vampire star goes supernova first, the sudden loss of mass could fling the surviving companion away at incredible speed, a runaway star rocketing through the galaxy. Alternatively, if the binary survives the first explosion, we might witness the rare and cataclysmic spectacle of a paired supernova, where one star's detonation triggers the collapse of its still-bound partner. In the realm of massive stars, companionship is not about peace, but about perpetual, gravity-warping conflict that reshapes destinies and forges the universe's most bizarre objects. This constant internal and external violence makes massive stars profoundly unstable, prone to fits of cosmic rage and breathless, rhythmic pulsations. Among the most volatile are the luminous blue variables, stars living on the very edge of self-destruction. Think of them as stellar pressure cookers, their immense radiation constantly battling to escape their own gravity. For decades or even centuries, an LBV might shine with a steady, ferocious blue light. Then, without clear warning, it can erupt. The star undergoes a giant outburst, not a supernova but a titanic stellar tantrum. It violently ejects a shell of its own outer layers, equivalent to several times the mass of our Sun, into space. During these eruptions, the star's appearance transforms completely. As the ejected material expands and cools, it shrouds the hot blue core, making the entire system look like a cooler, larger, and redder star. The original star is still there, blazing away inside its own self-made cocoon. The classic example is P Cygni, a star that suddenly appeared in the sky in the year 1600, brightening to third magnitude before fading away. It has experienced several major outbursts since, each time casting off another shell of its atmosphere. Another, S Doradus, in a neighboring galaxy, fluctuates wildly in brightness as it goes through these cycles of eruption and quiescence. These are not stars calmly aging, they are stars actively, violently shedding their skin in preparation for their final collapse. Not all instability is explosive. Some massive stars breathe. Yellow hypergiants and red supergiants, having swollen to enormous sizes, often become pulsating variables. Their vast, tenuous outer layers are so loosely bound by gravity that they rhythmically expand and contract like the chest of a sleeping giant. The entire star, thousands of times larger than our Sun, literally swells and shrinks over periods of months or years. With each expansion, the surface cools and dims slightly. With each contraction, it heats and brightens. This pulsation is a sign of deep-seated turmoil, as the star's interior struggles to find equilibrium between the energy generated in its core and the radiation trying to escape. The most famous example might be the red supergiant Betelgeuse in Orion's shoulder, which famously dimmed by nearly 2/3 in 2019. While the leading explanation points to a giant cloud of dust ejected from the star, its regular, smaller pulsations are a constant feature of its unstable existence. Studying these rhythms is like taking the star's pulse, listening to the heartbeat of a dying giant. These instabilities are far more than just a spectacular light show. They are critical diagnostics, the final frantic signals a star sends before the silence. The eruptions of an LBV and the pulsations of a hypergiant represent the star's last, desperate attempts to stabilize itself as its core runs out of usable fuel. Each outburst strips away more mass, peeling back the onion layers to reveal the hotter elements beneath. By monitoring these changes in brightness, temperature, and size, astronomers can peer into the final chapters of a massive star's life story. They can estimate how much mass the star has shed, what elements are now exposed at its surface, and crucially, how much fuel remains in its doomed core. This allows scientists to make predictions, to point at a specific, violently variable star and say, this one is a prime candidate, its time is almost here. In this way, the erratic behavior of these stellar titans acts as a countdown clock, ticking toward the moment gravity finally wins the war and the core collapses, triggering the most energetic explosion in the modern universe. That final, frantic countdown leads us to a specific and rare class of stellar giants, the hypergiants. This title is not given lightly. It is reserved for the absolute pinnacle of stellar luminosity and mass, stars so extreme they exist in a state of perpetual crisis. If red supergiants are unstable, hypergiants are on the verge of coming completely unglued. They represent the most precarious, fleeting stages in a massive star's evolution, moments of such intense internal pressure that the star can barely hold itself together. We classify them by their color and temperature, which correspond to different phases of their death throes. Red hypergiants, like the famous UY Canis Majoris, are the swollen, cool behemoths. Having expanded to mind-boggling sizes after exhausting hydrogen in their cores, they are now fusing heavier elements in shells. Their surfaces are relatively cool, giving them a deep red hue, but their sheer scale makes them incredibly luminous. UY Canis Majoris is so vast that if placed at our Sun's position, its outer fringes would reach the orbit of Saturn. Yet it is not a placid balloon. It is violently ejecting massive clouds of dust and gas, shrouding itself in a cocoon of its own debris. Then there are the yellow hypergiants like Rho Cassiopeiae. These are even rarer and more unstable. They occupy a dangerous middle ground in temperature, no longer cool red giants but not yet hot blue variables either. This yellow phase is a terribly unstable equilibrium. Rho Cassiopeiae is known to undergo spectacular eruptions, suddenly dimming as it catapults a shell of material into space, then brightening again. Each of these outbursts can eject material equal to the mass of our entire planet. Finally, the blue hypergiants, like the star Eta Carinae's primary component, represent a hot, luminous, and equally volatile stage. They are searingly hot and blaze with a luminosity millions of times that of our Sun, driving those catastrophic stellar winds we discussed earlier. What unites all hypergiants, regardless of color, is their extreme instability and breathtaking rate of mass loss. They are not calmly aging, they are disintegrating in real time. A hypergiant can shed the equivalent of Earth's mass every year or even far more during eruptions. This furious shedding of their outer layers is a race against the core's collapse. Their rarity in the galaxy is a direct result of this behavior. A star only passes through the hypergiant phase for a brief sliver of its already short life, perhaps only a few 100,000 years before either collapsing or blowing itself apart. Spotting one is like catching a glimpse of a star in its final, most dramatic act, teetering on the knife's edge between existence and cosmic catastrophe. This ceaseless instability is not a private affair. The rage of a hypergiant and the fury of a massive star's final days ripple outward, shaping the destiny of its entire galactic neighborhood. These stellar titans are the ultimate ecosystem engineers of galaxies, their brief lives dictating the birth, composition, and structure of everything that follows. Their primary tool is light, but not the gentle visible light we see. A massive star emits a torrent of high-energy ultraviolet radiation, photons so powerful they can strip electrons from hydrogen atoms, the most common element in the universe. This process, called ionization, transforms vast, cold clouds of molecular gas into glowing, cavernous structures known as H2 regions or emission nebulae. The Orion Nebula is our local example, a stellar nursery lit up like a cosmic lantern by the fierce ultraviolet glare of just a handful of young, hot stars at its core. The radiation carves out cavities within the cloud, compressing the surrounding gas into dense pillars and walls. Within these compressed borders, the seeds of new stars are sown as gravity finds it easier to collapse the denser material. In this way, the violent light of massive stars does not just illuminate the nursery, it actively sculpts it, triggering a second wave of star formation along the edges of the bubbles they create. But light is only the beginning. The hurricane-force stellar winds we discussed earlier act as cosmic bulldozers. These supersonic outflows slam into the surrounding interstellar medium, sweeping up gas and dust into massive, expanding shells. These shells can collapse under their own gravity, fragmenting into new clusters of stars, or they can gather material for millions of years, eventually becoming the birthplaces of future solar systems. The star, through its wind, is physically rearranging the architecture of its galaxy. The final and most dramatic act of engineering is the supernova explosion. When the core collapses, the resulting shockwave does more than just create a neutron star or black hole. It catapults the star's entire outer layers, now enriched with freshly forged heavy elements like carbon, oxygen, silicon, and iron, into the void at speeds approaching 1/10 the speed of light. This ejected material, glowing brightly for thousands of years as a supernova remnant, mixes violently with the interstellar medium. It is a cosmic delivery service, seeding the galaxy with the raw ingredients for rocky planets, organic molecules, and life itself. The shockwave from the blast also travels outward, compressing nearby gas clouds with even greater force than the stellar wind, often triggering a starburst, a frenzied episode of new star formation. Our own solar system is believed to have formed from a cloud of gas enriched by the explosions of several previous generations of massive stars. The iron in your blood, the calcium in your bones, and the oxygen you breathe are all gifts from stars that died billions of years ago. Without these titanic stellar lives and deaths, galaxies would be sterile places, filled only with hydrogen and helium, devoid of the complex chemistry that builds worlds and ultimately us. Their legacy is written in the very fabric of the galaxy and in the atoms of our own bodies. The final silence of iron in the core is a death sentence. For millions of years, the star's furious fusion has been a constant outward push, a nuclear fire holding back the crushing weight of its own outer layers. But iron ash cannot burn. It accumulates, a cold, inert ball of doom at the star's very heart. When this iron core grows too heavy, roughly 1.4 times the mass of our Sun, the delicate balance of forces that has sustained the star for its entire life shatters in an instant. Gravity, unopposed at last, wins the war. What happens next is one of the most violent events in the known universe, a core collapse supernova. The collapse is terrifyingly fast. In less than a second, the core, which is about the size of Earth, implodes under its own weight. Electrons are literally crushed into protons, forming neutrons and releasing a flood of ghostly particles called neutrinos. The core becomes an unimaginably dense sphere of pure neutrons, a proto-neutron star only about 12 miles across. The collapse halts so abruptly that the inrushing material from the outer layers rebounds off this new, ultra-hard surface. This rebound creates a titanic shockwave that races back outward through the still collapsing star. At this critical moment, the flood of neutrinos, carrying away 99% of the explosion's energy, plays a vital role. They deposit just enough energy into the shockwave to reignite it, turning the inward collapse into a catastrophic outward explosion. The rebounding shockwave blasts through the star's outer layers at speeds exceeding 45 million miles per hour, ripping the entire stellar structure apart from the inside out. This is a Type II supernova if the star still had its hydrogen envelope, or a Type 1b or C if fierce stellar winds had already stripped it bare. The energy release is beyond comprehension. For a few weeks, this single exploding star can outshine the combined light of every other star in its entire host galaxy. Within the unimaginable heat and pressure of this expanding fireball, the universe forges its heaviest elements. The rapid neutron capture process, or R process, occurs. Atomic nuclei are bombarded by a dense sea of free neutrons in the seconds following the core collapse, allowing them to capture neutrons faster than they can radioactively decay. This builds up elements heavier than iron, like gold, platinum, uranium, and silver. Every piece of jewelry, every electronic component that relies on rare earth elements, contains material created in the heart of a dying star's final cataclysm. The supernova scatters these newly forged elements across light years of space, where they will eventually mix into clouds of gas and dust, becoming the raw materials for new stars, planets, and perhaps future life. The star's death is not an end, but a spectacular elemental rebirth. Yet even the awesome fury of a supernova is not the final word. For the absolute heaviest stellar champions, those born with masses exceeding perhaps 40 times that of our Sun, death arrives in a form so cataclysmic it redefines the word explosion. This is the hypernova, a supernova on cosmic steroids. While a typical core collapse supernova releases a staggering amount of energy, a hypernova can be up to 100 times more powerful. The key difference lies not in the fuel but in the engine. A hypernova requires a special kind of stellar corpse, a rapidly spinning, incredibly massive core that collapses directly into a black hole. As this core implodes, its immense rotational energy is focused into two narrow, opposing beams or jets that scream outward at nearly the speed of light. These jets, composed of ultra-hot plasma and radiation, act like cosmic blowtorches, drilling through the star's outer layers and erupting into space. If one of these relativistic jets is pointed directly at Earth, we witness the single most powerful burst of energy in the modern universe, a gamma-ray burst. For a few seconds, or sometimes several minutes, this narrow beam of pure, high-energy gamma radiation can outshine every other source of gamma rays in the cosmos combined, releasing more energy than our Sun will emit in its entire 10 billion-year lifetime. The power is almost incomprehensible. A single gamma-ray burst from a galaxy billions of light-years away can temporarily outshine the rest of the entire gamma-ray sky. But such a focused beam is also a weapon of unimaginable range. If a star within our own galaxy, a few thousand light-years away, were to point its death scream directly at us, the consequences would be apocalyptic. The initial blast of gamma rays would not just pass through our atmosphere, it would rip it apart. The high-energy radiation would break apart nitrogen and oxygen molecules, generating vast amounts of nitrogen dioxide, a brownish gas that would shroud the planet in a toxic smog, blotting out the sun and triggering a rapid global winter. The ozone layer, our shield against the sun's ultraviolet rays, would be obliterated. The ensuing cascade of chemical and climatic disasters could trigger a mass extinction event on a scale not seen for hundreds of millions of years, effectively sterilizing our side of the planet. This is not science fiction. It is a sobering physical possibility written into the life cycle of the universe's most massive stars. Their final moments are not merely self-destruction. They are directional eruptions of pure energy capable of influencing the fate of life across interstellar and perhaps even intergalactic distances. The cataclysmic fury of a supernova leaves more than just an expanding cloud of glowing debris. At the very heart of that chaos, a new and bizarre object is born from the collapsed core. If the remaining stellar corpse weighs between about 1.4 and 3 times the mass of our Sun, gravity will crush it into one of the universe's most extreme forms of matter, a neutron star. This is not a star in any traditional sense. It is the final, dense cinder of a giant's heart, compressed to an almost unreal state. The forces at work here rewrite the rules of atomic structure. During the core's catastrophic collapse, the immense pressure is so overwhelming that it forces electrons and protons to merge, transforming into neutrons. The entire object becomes a city-sized sphere of pure nuclear material, a single, gigantic atomic nucleus. To grasp its density, consider this. A single sugar cube's worth of neutron star material would weigh over 1 billion tons on Earth, as much as an entire mountain. This incomprehensible density creates gravity so powerful that if you could drop a marble from just 1 meter above its surface, it would slam into the crust at millions of miles per hour. Some of these neutron stars reveal themselves in a spectacular and rhythmic way as pulsars. These are neutron stars born spinning at incredible speeds, often completing hundreds of rotations every single second. They possess magnetic fields trillions of times stronger than Earth's, which funnel their energy into 2 narrow, powerful beams of radiation that shoot out from their magnetic poles. If the star's spin axis is tilted relative to its magnetic axis, these beams sweep through space like the blinding rays of a cosmic lighthouse. And if that lighthouse beam happens to sweep across our line of sight here on Earth, we detect a regular, repeating pulse of radio waves, light, or even X-rays with each rotation. The most famous example is the Crab pulsar, the spinning heart of the Crab Nebula. This nebula is the expanding wreckage from a supernova that was so bright it was recorded by Chinese and Arab astronomers in the year 1054 AD, visible in the daytime sky for weeks. Today, at the very center of that beautiful, tangled nebula, the Crab pulsar spins 30 times every second, flashing its beacon with metronomic precision. Each pulse we detect is a direct signal from this tiny, ultra-dense remnant, a relentless heartbeat marking the grave of a star that died nearly 1,000 years ago. These celestial lighthouses serve as precise cosmic clocks, allowing astronomers to probe the nature of gravity and spacetime itself. But a neutron star represents a pause in gravity's victory, not its final triumph. For the universe's absolute heaviest stellar corpses, the collapse continues past any conceivable limit. When the remnant core left behind after a supernova exceeds roughly 3 times the mass of our Sun, no known force in physics can possibly halt its descent. Not the repulsion of atomic nuclei, not the pressure of degenerate neutrons, nothing. At this threshold, gravity achieves total, absolute victory, and a stellar mass black hole is born. The core crushes down to a mathematical point of infinite density called a singularity, a place where our current laws of physics simply cease to function. Surrounding this point is the event horizon, a spherical boundary of no return. It is not a physical surface, but a point in space where the escape velocity exceeds the speed of light. Since nothing, not even light, can travel that fast, anything crossing that threshold is lost forever to our observable universe. The star's core vanishes from sight, leaving behind only its immense gravitational pull. So how do we find an object that emits no light? We watch for the violent ballet it forces upon its surroundings. The most common way we detect these stellar mass black holes is in binary systems, where the black hole orbits a normal, luminous star. One of the most famous examples is Cygnus X1, a system thousands of light years away in the constellation Cygnus. Here, a blue supergiant star is locked in a tight, deadly dance with an invisible companion about 15 times the mass of our Sun. The black hole's immense gravity pulls a continuous stream of gas from the outer atmosphere of its giant partner. This stolen material does not fall straight in. Instead, it forms a whirling, flattened disk around the black hole called an accretion disk. As the gas spirals inward at tremendous speeds, particles collide violently, generating intense friction that heats the disk to temperatures of millions of degrees. It is this superheated plasma just outside the event horizon that glows not in visible light but in high-energy X-rays. By observing these telltale X-ray flares and measuring the wobble of the visible star, astronomers can calculate the mass of its invisible companion. When that mass far exceeds the neutron star limit, the only possible explanation is a black hole. These X-ray binaries are cosmic lighthouses, their fierce glow signaling the presence of an invisible monster hiding in plain sight, a permanent tombstone for a star that was once among the galaxy's most massive and brilliant. That precise, pulsing heartbeat from a neutron star is a cosmic metronome, but there is another, more expansive way massive stars serve as the universe's timekeepers and mapmakers. Their predictable brilliance allows them to become something far more useful than spectacular objects of study. They transform into fundamental tools for measuring the cosmos itself. This is the principle of the standard candle, a celestial object with a known intrinsic brightness. If you know how bright a star truly is, and you measure how dim it appears from Earth, you can calculate exactly how far away it is. It is like seeing a familiar 100-watt light bulb in the distance. The fainter it looks, the farther away you know it must be. For nearby galaxies, the most famous of these standard candles are Cepheids variables, stars that rhythmically pulsate with a period directly tied to their true luminosity. However, Cepheids are not typically the most massive stars. They are intermediate in mass. To reach across the vast gulfs between galaxies, astronomers need a brighter beacon. This is where the true titans come in. Certain classes of hypergiants and the most luminous supernova provide that crucial, long-distance signal. For instance, the violent luminous blue variables and the rarest, most unstable yellow hypergiants have characteristics, like their temperature and the details of their light spectra, that correlate tightly with their maximum possible brightness. By identifying one of these stellar giants in a distant galaxy and analyzing its light, astronomers can deduce its true power output and from there its distance. Even more powerfully, a specific type of supernova known as a Type 1a, though originating from a different stellar process involving white dwarfs, provides a remarkably consistent peak brightness that has been instrumental in measuring the farthest reaches of the universe. But core collapse supernova from massive stars, particularly those that have been stripped of their hydrogen envelopes, are also being refined as standard candles. Their explosion brightness is linked to how quickly their light fades, a relationship that allows for distance calculation. It was by using these brilliant, dying stars as mile markers that astronomers made one of the most profound discoveries of the 20th century, the accelerating expansion of the universe. By measuring distances to incredibly far-off galaxies and seeing how fast they were receding, they found that the universe is not just expanding, but that the expansion itself is speeding up, driven by a mysterious force we now call dark energy. Without the predictable demise of these massive stars serving as our cosmic yardsticks, we would be lost in a universe without a scale, unable to grasp its true size, history, or ultimate fate. These cosmic yardsticks we use today are the descendants of a much earlier, more violent generation. To find the true origin of the universe's most massive stars, we must journey back to the very beginning, to a time before galaxies, before planets, before even the first heavy atoms. This is the era of the first stars, a generation astronomers call Population 3. They were the cosmic pioneers, forming from a universe that was nothing but pristine hydrogen, helium, and a trace of lithium, the only elements forged in the Big Bang itself. This purity had a profound consequence. Without heavier elements like carbon and oxygen to help radiate heat away, the collapsing clouds of gas could not fragment easily. There were no dust grains to shield parts of the cloud or help it cool. The result was a runaway collapse that funneled a staggering amount of material into a single, monstrous core. Theorists believe population 3 stars were almost unfathomably massive, likely ranging from 100 to 1,000 times the mass of our Sun. They were born as true cosmic titans, shining with a ferocious, ultraviolet brilliance that had never before illuminated the cosmos. Their internal structure was different too. With no heavier elements to create opacity, their interiors were more transparent, allowing radiation to flow outward with less resistance. This might have helped them temporarily stabilize despite their extreme mass, but it also meant they burned their fuel at a truly suicidal pace. A star several hundred solar masses would have lived a breathtakingly short life, perhaps only 1 or 2 million years. Its end would have been as unique as its birth. When such a star finally exhausted its nuclear fuel, its core would have been so massive that no supernova shockwave could possibly reverse its collapse. Instead of a brilliant, element-scattering explosion, the entire star would have imploded directly, catastrophically, into a black hole. It would have simply vanished from the universe, leaving behind a gravitational pit and perhaps a faint whisper of radiation. This silent fate is crucial, because they collapsed without the classic supernova that enriches space with heavy elements. The death of a population 3 star was a cosmic dead end for chemistry. It took later generations of slightly smaller, metal-poor stars to finally explode and seed the universe with the carbon, oxygen, and iron needed to build everything that followed, including us. The hunt for these first stars is one of astronomy's greatest challenges. They lived and died so long ago, over 13 billion years in the past, that their direct light is incredibly faint and redshifted into the infrared. Our best hope is to catch indirect signatures, perhaps the shadow of one as it passes in front of an even more distant quasar, or the unique chemical fingerprint they left in the atmospheres of the oldest stars we can see in our own galaxy. Finding evidence of population 3 would be like discovering the fossil of a cosmic dinosaur, giving us a direct glimpse into the universe's violent, luminous, and profoundly simple childhood. The silent collapse of the first stars left a universe still hungry for the elements of life. That crucial task fell to the next generation, stars that learned to die with spectacular violence. And in their final act, some of these giants reveal their deepest secrets by literally tearing off their own skin. These are the Wolf-Rayet stars, cosmic entities so stripped bare they glow with the searing light of their own exposed hearts. If a red supergiant is a star swollen to its maximum size, a Wolf-Rayet star is its opposite, a star peeled down to its core by its own ferocious power. They begin their lives as typical massive stars, but their tremendous luminosity drives stellar winds of almost unimaginable force. These are not the gentle breezes of our Sun, but continuous, supersonic hurricanes blasting away at several million miles per hour. Over a relatively short period, perhaps just a few 100,000 years, these winds act like a cosmic sandblaster, relentlessly scouring away the star's entire outer hydrogen envelope. What remains is a naked, blazing core. The star's surface, now deprived of its hydrogen cloak, is a fusion furnace laid bare. It is an exposed stellar engine, fusing helium into heavier elements like carbon, nitrogen, and oxygen at a furious rate. The temperatures at the surface are staggering, often exceeding 90,000 degrees Fahrenheit, making them some of the hottest stars known. This extreme heat and the powerful winds create a signature that astronomers can spot across vast distances. When we analyze the light from a Wolf-Rayet star, we don't see the normal dark absorption lines of a typical star's spectrum. Instead, we see brilliant, broad emission lines. These are bright bands of color caused by the excited atoms of helium, carbon, and nitrogen being violently ejected in the stellar wind. The lines are broad because the gas is moving so fast, both toward and away from us, that the light is Doppler shifted across a wide range. It is the spectroscopic fingerprint of a star blowing itself apart in real time. This makes them prolific, if unexpected, dust producers. In the turbulent outflow where hot gas from the star meets cooler interstellar material, carbon atoms can link together, forming soot-like grains. These stars are essentially cosmic factories for carbon-rich dust, spreading it into the galaxy. But this exposed, unstable state cannot last. A Wolf-Rayet star represents one of the final chapters before a supernova. Having already shed its hydrogen, it is a prime candidate for a Type 1b or Type 1c supernova, a core collapse explosion that will lack the hydrogen signature in its aftermath. More intriguingly, some of the most massive Wolf-Rayet stars, particularly those with rapidly rotating cores, are the leading candidates for the progenitors of long gamma-ray bursts. When such a star finally collapses, its spin can focus the explosion into those devastating relativistic jets. So when we observe a Wolf-Rayet star, we are looking at a stellar countdown in its final minutes. We are seeing the raw engine of element creation, unveiled and raging, moments before it triggers a cataclysm that will seed the future. That stellar wind is a gentle breeze compared to the magnetic fury of a magnetar. This is a rare and terrifying breed of neutron star, the ultimate expression of a magnetic field in our universe. While all neutron stars possess unthinkably strong magnetism, a magnetar takes this to an almost mythical extreme. Its magnetic field is not just strong, it is 1,000 trillion times more powerful than the magnetic field that protects our planet. To grasp that scale, if a magnetar were located halfway between the Earth and the Moon, its magnetic pull would be powerful enough to strip the data from every credit card on our planet. These objects are not born from just any supernova. They are the cinders of massive stars that were themselves highly magnetic, spinning rapidly as they died. When such a star collapses, its already intense magnetic field is compressed along with its matter, amplifying it to these ludicrous levels. The result is a cosmic monster of pure force. The unimaginable stress of this magnetic field warps the magnetar's solid crust, which is a lattice of iron nuclei, into a rigid, crystalline structure. But this crust is not perfectly stable. As the magnetic field evolves and twists, it exerts titanic stresses, causing the crust to crack and shift in events known as starquakes. The energy released in a single one of these stellar convulsions is beyond human comprehension. In 1/10 of a second, a magnetar starquake can unleash more energy than our sun will radiate across 100,000 years. This catastrophic release often manifests as a giant flare, a burst of gamma rays and X-rays so intense it can briefly outshine every other source in the Milky Way. The most famous recorded event occurred in 2004, when a magnetar 50,000 light-years away in the constellation Sagittarius flared with such power that its radiation, though harmless by the time it reached us, actually compressed Earth's upper atmosphere and briefly disrupted long-range radio communications. It was a palpable reminder that these distant magnetic ghosts can reach out and touch us across galactic distances. As the most intensely magnetic objects known, magnetars represent the ultimate victory of force over form, where the very fabric of a star is dominated not by gravity or heat, but by an invisible, universe-bending field. Magnetars represent one extreme outcome of stellar death, but another, quieter mystery haunts our observations of massive stars. Astronomers face a persistent and puzzling gap between theory and reality called the red supergiant problem. Our models of stellar evolution tell a clear story. A star 8 to 40 times the mass of our Sun should spend its final million years as a swollen, cool red supergiant like Betelgeuse. When these stars finally exhaust their fuel and collapse, they should produce a specific type of brilliant supernova, a Type 2, marked by strong hydrogen signatures in their light. Therefore, when we look at galaxies where supernovae have recently occurred, we should be able to look back at archival images and see the red supergiant that was there before the explosion. Yet, when astronomers conduct this cosmic detective work, they come up short. In a majority of cases, the star that was there before the supernova is simply missing. The predicted red supergiant progenitor is not visible. This discrepancy is not a minor accounting error. It suggests a fundamental gap in our understanding of how these giants spend their final days and meet their end. Several compelling and unsettling theories have emerged to explain this vanishing act. The first possibility is one of cosmic camouflage. Red supergiants are prolific producers of dust, casting off their outer layers in great clouds of carbon and silicate grains. Perhaps in their final centuries, these stars shroud themselves in such thick, localized cocoons of dust that they become effectively invisible at the wavelengths our telescopes typically use for these pre-explosion searches. We might be looking right at them but seeing only a dark, obscuring shroud. A second, more dramatic explanation points to a completely different fate: the failed supernova. In this scenario, the star does everything it is supposed to do, evolving into a red supergiant and building an iron core. But when that core collapses, something goes wrong. The rebounding shockwave, for reasons not fully understood, stalls and fails to rip the star apart. Instead of a brilliant supernova, the entire star implodes directly into a black hole. From the outside, you would see the red supergiant simply wink out of existence. It would fade from view as its outer layers fall into the newborn black hole, leaving behind no spectacular light show, only a faint infrared glow from any remaining accreting material. There is tantalizing, though rare, observational support for this idea. In 2015, astronomers watched as a star in a distant galaxy, previously catalogued as a red supergiant, suddenly flared in infrared light and then permanently faded from view in optical light, a signature consistent with a failed supernova. A third possibility is that our stellar models are incomplete. Maybe the late-stage evolution of these stars is more complex, involving intense mass loss or binary interactions that strip the star down before it can become a classic red supergiant, causing it to explode as a different, hotter, and less predictable type of supernova. The red supergiant problem is more than an academic curiosity. It is a direct challenge. It forces us to question whether we truly understand the final moments of the stars that forge the elements of our world. Each missing progenitor is a silent question mark, hinting that the death of a giant can be far stranger and far quieter than our most dramatic theories allow. That silent question mark hanging over a red supergiant's fate does not erase the profound legacy it leaves behind. When a massive star does succeed in exploding, it performs the universe's most vital act of cosmic alchemy. The supernova is not merely a spectacular death, it is the ultimate delivery system, scattering the star's elemental harvest across light years of space. Within that expanding fireball are all the heavy elements forged during the star's life and in its final cataclysm: carbon and oxygen, the backbones of life and water; silicon and sulfur, the raw materials of rock and planet; iron and nickel, the molten cores of worlds. These are not destroyed in the blast, they are violently ejected, mixed, and seeded into the surrounding clouds of gas and dust. This enriched material becomes the feedstock for the next generation of stars, and crucially, for the planets that will form around them. Our solar system coalesced from just such a cloud, one that had been fertilized by the explosions of several massive stars that died billions of years before the Sun was born. But the story goes deeper than the elements forged during the star's stable life. The most precious, heaviest elements require an even more extreme birth. In the chaotic seconds following the core collapse, within the superhot supernova ejector itself, or in the violent collisions between neutron stars, a frantic process unfolds called rapid neutron capture, or the R process. Here, atomic nuclei are bombarded by an immense flood of free neutrons. They capture these neutrons faster than the resulting unstable isotopes can radioactively decay, rapidly building up heavier and heavier elements. This is how the universe manufactures gold and platinum, uranium and iodine, neodymium and silver. Every ounce of precious metal in a wedding ring, every trace of iodine essential for human metabolism, every gram of uranium that powers reactors was created in these moments of unimaginable stellar violence. The iron in your blood that carries oxygen, the calcium in your bones that gives them strength, the phosphorus in your DNA that holds the code of life, none of these existed at the dawn of the universe. They were built in the hearts of stars and scattered by their explosive deaths. Every single atom in your body, except for the primordial hydrogen, was once part of a star. And for the crucial elements that make rocky planets and complex chemistry possible, massive stars are the primary, indispensable source. We are, in the most literal sense, stardust that has learned to look back at the sky and wonder about its own origin. That legacy of cosmic creation comes with a terrifying asterisk. A massive star is not just a generous benefactor, it is a profoundly dangerous neighbor. For any planetary system unlucky enough to form within its sphere of influence, the presence of such a titan spells almost certain doom. The danger begins long before the star dies. Its blistering ultraviolet radiation is a constant, erosive force. For a young planet with a nascent atmosphere, this high-energy light acts like a sandblaster, striking molecules in the upper air and giving them enough energy to escape the planet's gravity entirely. Over millions of years, a world that might have been a potential cradle for life could have its atmosphere and oceans completely stripped away, leaving behind a barren, irradiated rock. This is compounded by the star's powerful X-ray flares, which can penetrate deeper, ionizing the atmosphere and potentially breaking down the complex chemistry needed for biology to arise. The star's fierce stellar wind, a supersonic stream of charged particles, adds to the assault, relentlessly scouring the space around it and pushing the protective magnetic bubbles of any nearby planets to their limits. A planet orbiting in what we might call the habitable zone of such a star would find the title bitterly ironic, its surface bathed in a sterilizing glow. But this ongoing bombardment is merely the prelude to the main event. The ultimate planetary catastrophe is the star's death. A supernova explosion within a few dozen light years would be an existential threat. The initial flash of ultraviolet and X-rays would be followed by an expanding shell of high-energy particles and debris moving at a significant fraction of light speed. For a planet like Earth, the effects would be apocalyptic. The gamma-ray and X-ray burst alone would chemically rip apart the upper atmosphere, destroying the ozone layer that protects life from the sun's own ultraviolet radiation. The planet would be bathed in deadly levels of UV for years, devastating ecosystems both on land and in the sea. The incoming cosmic rays from the expanding shockwave could increase mutation rates and trigger long-term climate change. There is evidence in Earth's own geological record that such events may have occurred in the distant past. Layers of sediment rich in radioactive isotopes like iron-60, which is forged only in supernova, suggest our planet was sprinkled with stellar debris around 2.5 million years ago, coinciding with a minor extinction event and a period of global cooling. A much closer supernova, or worse, a gamma-ray burst whose beam was pointed directly at us, could cause a mass extinction on the scale of the event that wiped out the dinosaurs. Astronomers refer to the lethal range around such an explosion as a kill zone, a spherical volume of space where complex life would be severely threatened or erased. Thankfully, our solar system currently resides in a relatively quiet galactic suburb, with no massive stars poised to explode in our immediate vicinity. But we can watch future candidates from a safe distance. The runaway star Wolf-Rayet 124, a massive star that has already shed its outer layers and is racing through space, is one such ticking time bomb. It will certainly end its life in a supernova, possibly a gamma-ray burst, but it is thousands of light years away, posing no threat to us. Its brilliant, violent demise will simply be a spectacle for future astronomers, a stark reminder that the same forces that gift the universe with the elements of life also hold the power to erase it. The universe's most dangerous fireworks also represent one of astronomy's greatest observational puzzles. Studying these rare, fleeting giants is an exercise in cosmic frustration, a constant battle against distance, distortion, and darkness. The first and most pervasive enemy is interstellar dust. Those beautiful, glowing nebulae that cradle young stars are also made of microscopic grains of carbon and silicate, the same material that shrouds dying hypergiants. This dust doesn't just block light, it absorbs and scatters it, a phenomenon astronomers call extinction. The shorter, bluer wavelengths of light from a hot, young massive star are especially vulnerable, often being completely filtered out before they reach our telescopes. What arrives is a reddened, dimmed version of the star's true light, like trying to identify a bright blue beacon through thick, dirty fog. This makes accurately measuring a star's temperature, size, and true brightness incredibly difficult, leading to the frequent revisions in the rankings of the largest and most massive stars. Our own atmosphere adds another layer of distortion. The constant churning of air acts like a wobbly lens, blurring the fine details of distant stars, a problem known as seeing. This is why observatories are built on high, dry mountains, but even the best ground-based sites cannot eliminate the problem entirely. To truly understand these stellar engines, we cannot rely on visible light alone. A massive star's life story is written across the entire electromagnetic spectrum. Its searing ultraviolet radiation emitted from its furious surface tells us about its temperature and powerful winds. X-rays, often generated in colliding stellar winds or from hidden companion black holes, reveal its most violent interactions. The infrared light, which penetrates dust clouds far more easily than visible light, shows us the hidden structure of stellar nurseries and the warm envelopes of dying giants. Radio waves can trace the cold molecular gas from which stars form and map the expanding shells of ancient supernova remnants. Piecing together this multi-wavelength puzzle is the only way to get a complete portrait. This immense challenge is now meeting its match in a new generation of space-based observatories, led by the revolutionary James Webb Space Telescope. Unlike Hubble, which primarily sees invisible and ultraviolet light, Webb is an infrared specialist. Its colossal gold-coated mirror and ultra-sensitive instruments are designed to peer directly through the veils of dust that have hidden so much of stellar evolution from our view. For the first time, we can stare into the hearts of dense stellar nurseries like the pillars of creation and watch massive stars being born in real time, seeing the intricate details of accretion disks and the powerful jets they launch. Webb can analyze the chemical makeup of a star's wind or a supernova's ejector with breathtaking precision, identifying the specific elements being forged and scattered. It is already searching for the chemical fingerprints of those elusive first-generation population, 3 stars in the most distant early galaxies. Every new image and spectrum from Webb is not just a pretty picture. It is a data stream that promises to solve long-standing mysteries, from the true upper mass limit of stars to the final, hidden years of a red supergiant's life. With these new eyes on the cosmos, we are no longer just observers of these distant giants. We are becoming witnesses to their most intimate secrets. The James Webb Space Telescope is just the beginning of a new era of cosmic vision. Our next generation of observatories will not merely look at these stellar titans, they will dissect them with a precision we once thought impossible. On a mountaintop in Chile, engineers are constructing the eye of a new giant, the extremely large telescope. Its primary mirror will measure an astonishing 39 meters across, a light-gathering surface so vast it will collect more light than all of the major optical research telescopes on Earth today combined. This is not just an incremental upgrade, it is a leap into a new realm of detail. With this instrument, astronomers will do something previously reserved for our Sun. They will directly image the surface of red supergiants in other galaxies. We will no longer see Betelgeuse as a single point of light, but as a resolved disk, watching in real time as colossal convection cells bubble and churn across its seething atmosphere. We might witness the formation of giant star spots or see the vast plumes of dust that shroud these stars in their final years. This telescope will also peer into the dusty disks around young massive stars, potentially catching the very birth of gas giant planets in these extreme environments, testing whether solar systems can form in the violent neighborhood of a stellar giant. But to understand the final, most violent moments of these stars, we must listen rather than look. This is the promise of gravitational wave astronomy. Facilities like LIGO and Virgo have opened an entirely new sense, detecting not light, but the ripples in spacetime itself caused by cataclysmic events. Their greatest hits so far have been the collisions of black holes and neutron stars, the dense remnants of massive stars. Each chirp and ring-down captured by these detectors is a direct signal from the final second of a binary star system's life, a pair of stellar corpses that spiraled together and merged after billions of years. By analyzing these waves, scientists can weigh the black holes and neutron stars with exquisite accuracy, providing a census of stellar corpses that tells us about the lives of the stars that created them. The future will bring even more sensitive detectors like the space-based LISA mission, which will hear the lower frequency hum of supermassive black hole mergers, tracing the lineage of stellar building blocks back to the cosmic dawn. The convergence of these technologies, the immense eyes of the ELT, and the profound ears of gravitational wave observatories promises to shatter our current models. We may discover that the upper mass limit for stars is far higher than we thought, or that hypergiants undergo internal processes we cannot yet conceive. We might finally catch a population 3-star in its death throes, or witness a supernova mechanism so strange it rewrites our textbooks. The history of astronomy teaches us that every time we build a new window on the universe, we are humbled by what we did not know. The next decade of observation will likely reveal that our current catalogue of stellar oddities, from magnetas to Wolf-Rayet stars, is merely a preliminary list. The true nature of the universe's most massive stars and the full scope of their chaotic, creative, and destructive power is waiting just beyond the edge of our current sight. The final, explosive echo of a supernova is a chemical signature written in light. This is how massive stars become the ultimate time capsules, preserving a galactic history that would otherwise be lost to deep time. When astronomers point their telescopes at one of these giants, they are not just seeing a ball of plasma, they are reading a cosmic biography. The most powerful tool for this is spectroscopy, the art of breaking a star's light into a rainbow of colors. Within that spectrum are dark lines like unique fingerprints, each corresponding to a specific element in the star's outer atmosphere. By analyzing these lines, scientists can perform stellar archaeology. They can determine the precise cocktail of elements that make up the star, from the primordial hydrogen and helium to the heavier metals forged in previous generations. This composition is a direct record of the environment in which the star was born. An ancient, massive star found in the sparse halo of our Milky Way, for instance, will show a severe lack of heavy elements. Its light tells us it formed from nearly pristine gas over 10 billion years ago, when the galaxy itself was just assembling from primordial clouds. Studying such stars gives us a snapshot of the universe's chemical infancy, a time before many supernovae had enriched the cosmos. In stark contrast, a young, brilliant star blazing within a spiral arm like Orion's will show a spectrum rich with metals. Its light reveals it was born from gas that had been recycled through many generations of stellar lives and deaths, seeded with the carbon, oxygen, and iron necessary for rocky planets. By mapping the compositions of massive stars across a galaxy, astronomers can literally chart its chemical evolution. They can see how the galactic core became enriched faster than the outer edges, trace the flow of material from supernova blasted bubbles into new nurseries, and even identify stars that were likely born in smaller, devoured galaxies, now orbiting as chemical immigrants within our own. Every massive star, from the oldest metal-poor relic to the youngest blue-white beacon, is a page in this ongoing story. Their collective lives and deaths are the pen that writes the chemical narrative of the cosmos, element by element, generation by generation, building from the simplicity of the Big Bang toward the breathtaking complexity we see today. That chemical narrative, written in starlight, is the ultimate legacy of these celestial giants. We began this journey with a star so vast it could swallow our solar system, UY Scuti, a monument to sheer physical scale. We then met the true heavyweight R13601, a monster of mass that burns with the fury of millions of suns. We followed these titans from their violent births in crowded stellar nurseries, through their frantic million-year lives spent in a desperate sprint from hydrogen to iron. We witnessed their volatile personalities, from the self-stripping winds of Wolf-Rayet stars to the rhythmic pulsations of hypergiants teetering on the edge. We stood in awe of their catastrophic deaths, the supernova and hypernova that forge gold and scatter the elements of life across the galaxy, leaving behind neutron stars, magnetars, and the ultimate gravity wells, black holes. Through every fact, a central truth emerges. These are not merely distant points of light. They are the fundamental engines of cosmic evolution. They manufacture the atoms of planets and people. They shape the structure of galaxies with their light, their winds, and their explosive finales. They constantly challenge the limits of our physics, asking how something can be so massive without tearing itself apart, or vanish without the explosion we predicted. Our very existence is a footnote in the life cycle of a massive star. The iron in your blood, the calcium in your bones, the oxygen in every breath you take, was forged in a heart like theirs and scattered by a death like theirs. We are, in the most literal sense, the children of stars that lived fast, died young, and gifted the universe with complexity. Their story is our origin story. So we turn the question to you. On this journey through 25 facts about the universe's most massive stars, which single detail left you the most awestruck? Was it the sheer scale of UY Scuti, the suicidal pace of a hypergiant's life, or the terrifying power of a magnetar's starquake? Share your thoughts in the comments below, and if you want to keep exploring the deepest mysteries of the cosmos, be sure to subscribe for more journeys to the edge of understanding.